Today we're jumping back to exercise 4C, and we're really going to see the significance of it and why they've sort of ordered, well, in my opinion, they've ordered it a bit poorly, because we're going to be using skills we've learned in 4G, okay? Now they introduced them in 4C, and we covered definite intervals in 4G, but I think it makes more sense to do G first. So the question says, find the area under the curve y equals 3x plus 2 from 0 to 5. So let's just talk about that first, like what it would mean. You know, it's the equation of a line, has a y-intercept of 5 and a slope of 3. And so you could find the area of this shape with a geometric argument, couldn't you? You know, you make a triangle and a rectangle, or you recognise it's a trapezium, and you calculate its base and its height, etc. You could do that. And that's what we were doing a little bit of in 4A. But now we're going to do integration methods. And the beauty of these integration methods is we can do it for curves. All right, so we're going to be finding the exact area under a curve using our integration methods. In 4A, we were talking about if we have a curve, you know, here's a curve, we were drawing rectangles underneath it and providing an approximation of the area. Now we're going to calculate the exact area. Okay, so the way we do that is the area, and this is the statement that's made there. Thank you. If you have the function f of x, okay, the area under the curve f of x will be the integral from a to b of f of x. All right, that's going to be the area under the curve of f of x over the interval a to b. So that means we want to know the area under 3x plus 2 here from 0 to 5. 3x plus 2. This is what we're going to evaluate. And so we learned those definite intervals last lesson, so there's nothing new, nothing outrageous what I'm going to perform right here. So that's going to be x squared, 3x squared on 2, plus 2x from 0 to 5. Okay, so what did I do there? The 3's hanging out. The integral of x is x squared on 2. The integral of 2 is 2x, and our boundaries from 0 to 5. Now when we perform it, we're going to be doing 3 times 5 squared on 2 plus 2 times 5, and then take away 0. It's fine to write it like that. When you sub-zero in, you can see all of this is going to go to 0. And then I've said, when you're going to calculate it, I mean this one's reasonably short, so you can do this manually, but when they're particularly long, it's much faster to put this in your calculator. And that way you can guarantee you're going to get the correct solution as well. But let's evaluate this here. We're going to have 3 times 25, so we're going to have 75 on 2, plus 10. So what's that, 32.5 plus 10, 42.5, or 95 on 2. And we're talking about area. So as soon as we're talking about area, we need to add that it's units squared. Okay, we've got square units under the x-axis, under the curve, 45. 42.5 square units. Okay, down the bottom of the page there, you'll see there's a number of properties, and one of the key questions of this exercise is getting you to prove those properties. And so this is one of them, all right? If you have the integral from a to b of just k, all right? K is a function, isn't it? It's like y equals k. Y equals k, it's just a number. What would it look like? Like here's the Cartesian plane. Here's k, right, has a y value of k, it's just going to be a horizontal line. So we're trying to prove, we're going to make this proof. So whenever we're doing a proof, we start with the left-hand side, we'll manipulate it, and then if we need to, we manipulate the right-hand side as well until they're equal to one another. This one we're not going to need to, we're just going to start with the left-hand side. So let's perform it. So we've got the integral from a to b of k with regards to x. Now when you integrate k, that becomes kx. Okay, and we're doing that from a to b. And then we use the fundamental theorem of calculus. This becomes k times b, take k times a, which is equal to k times b, take a, which is the right-hand side. Okay, so nice easy one there to prove. A lot of them make sense geometrically. So maybe I'll look at the properties and we'll just talk about them. So that's that table that's shaded in at the bottom. Okay, so the first one is a little bit difficult to illustrate geometrically, but you see, have a look at it, it says the integral from a to b is equal to the negative integral from b to a. So that means you can perform the integral back the other way, but it's going to give you a negative number. We've seen this one before already, of a, b of k times f of x. We can pull that number out the front. So that's k times the integral from a to b of f of x. So we've seen that one. This one, the integral from a to b of f of x plus the integral from b to c of f of x. So let's think about that. If we have this curve f of x, right? Here we've got x is a, here we've got x is b, and here we've got x is c. Okay? The integral from a to b of f of x is going to give you this area here. Alright, the integral from b to c of f of x will give you this area here. And the integral from a to c is going to give you the area of the whole thing. So you can see quite clearly the integral from a to b plus the integral from b to c will also equal the integral from a to c. So that's the third property. And then the fourth property is just we can integrate term by term. We can split it up into two integrals. Excellent. So let's have a go at 4c. I don't think there's a whole lot of questions we need to do from it. And then I've got some practice steps.